In this video, we propose a novel traversability estimator to conquer complex terrains. Let me briefly introduce the architecture. We start with a patchwise traversability value generation model that generates the distributions of the uncertainty and also roll and pitch angles. We first generate roll and pitch angles based on a quasi-static physics-based model. Then the velocity uncertainty is defined, involving the differences between commanded and actual velocities, represented as delta V and delta W. Thirdly, the pose prediction uncertainty is generated, which looks at differences between predicted and actual poses, specifically on X, Y, roll, and pitch. All the data is gathered through human teleoperation and refined using negative log likelihood loss. Next, we generate the ground truth traversability maps from the patchwise values. Here, two traversability maps are generated using estimated roll and pitch angles. In addition, 4 traversability maps are generated for the mean and standard deviation of velocity differences. Furthermore, 8 traversability maps are generated for the mean and standard deviation of pose differences. Moving on to mapwise traversability map reconstruction, we use the patchwise traversability values generated from the last stage to produce the final traversability map. The previously generated traversability values are combined with different weight vectors to produce the traversability map reconstruction labels. Finally, our traversability map estimator is trained to predict traversability maps based on the original elevation maps. We also show the performances of indoor and outdoor experiments. The TAL MPPI without TNT struggles on rocky terrain, while with TNT, it successfully navigates. Without TNT, MPPI relies on long, slow TAL rollouts to estimate terrain costs, which limits sample size due to computational constraints. This makes it harder for the robot to explore all possible paths and avoid non-traversable areas. With TNT, MPPI uses a shorter horizon, as the traversability map provides rich terrain information up front. This allows for faster, shorter rollouts that quickly find the best path through challenging terrain. We also deploy TNT in an outdoor, off-road environment, and TNT's traversability estimation can generalize to unseen terrain. The robot is able to avoid untraversable areas and explore potentially traversable ones, therefore successfully moving toward the goal.